All right, welcome back to Computer Science 50. This is the start of week 3. So we thought we'd begin by giving you some last tidbits of data from the surveys we conducted by way of sectioning. One of those questions you may recall was, why are you taking Computer Science 50? And among our favorite, or perhaps more amusing, answers were these. So to learn programming, so that's certainly compelling, if not to be expected. I need some skills. All right, fair enough, sort of the same idea. Tired of government. It's funny because that actually sort of resonates with me. Then we got such things as this. So it's funny, and I plucked this one out because at the lunches with David and TFs on Friday, one of our attendees actually mentioned that one of the things that apparently pushed him over the edge in taking the course was precisely this lure, this carrot of the problem sets apparently being so much fun at week's end. This, though, perhaps topped them all. So, and finally, what is the course's reputation on campus? So we made a concerted effort starting last year to try to flip on its head the course's reputation from being something scary and a lot of work to something that's exciting and fun and a lot of work. In answer to those changes, we got such responses from you all as these. Same student, though, elaborated. You know, you'd be surprised if you find Q guides and whatnot to be really tedious and boring. You'd be surprised how many of your classmates actually put some thought into their answers and try to catch the attention of the writers. Here we go. Not sure why it's 492, but it was an interesting takeaway. That is, I think, my favorite, Mozilla being the foundation that has made such software as Firefox and the like. So with that said, this week is less about syntax and less about C even, which we've hammered you with for the past couple of weeks, particularly those of you who had not yet seen such languages as this. And this week is more about problem solving. We'll come back to this teaser that we had in week 0 about ripping a phone book in half and then again and again. And think this week about how can you solve problems not only correctly, but also more efficiently. And we'll speak more to elements of design than we will necessarily correctness. And we'll also try to slap on this discussion some formality, so to speak, so that we have ways of expressing formally or even casually just how good your algorithm is, just how good your code is. It's one thing to write a program that returns correct values, but it's another to do it quickly, for instance. And those of you who tackled, say, the optimality problem in the hacker edition of Problem Set 1, which in contrast to the greedy solution required that you handled the cashier running out of certain denominations, which actually poses a problem because in the worst case, if you don't know a priori what kinds of coins you have available to you, and you try a greedy algorithm, well, you might recall from a footnote in the standard edition that bad things happen. And so the hacker edition of that problem set challenged students to actually work around those cases. But unfortunately, if you work around them without much thought, your code will run deathly slow, certainly for large inputs, if you take the approach of what we've been calling brute force solutions. So perhaps there are better designs still. So a couple of announcements. One new handout today, both slides and code, all in one. If you are among those who still have scratch boards in your possessions, the clock is ticking. Do be sure to get those to a teaching fellow per the original instructions with a little slip of paper in it with your name, ID number, and username. Problem set 2 in CS50.net. So we were quite excited and relieved this weekend to get this particular experiment out the door. So problem set 2, recall, is all about cryptography. And if you've not pulled it up just yet, this is the standard edition of that problem set. We hope it looks terribly exciting at first glance, if not a bit worrisome. If you flip through its pages, you will find that it first tasks you with, one, implementing kind of a silly song, but really as a warm-up. This Old Man, in fact, is this song, at least from my childhood, which has lots of repetition and lots of mappings from numeric numbers to actually English numbers and a couple of other syntactic features that are just useful to sort of warm up for the next two problems, which are far more interesting. The first being to implement your own version of the Caesar cipher, sort of a generalized case of ROT 13. And then following up to that would be an implementation of Visionaire, which is similarly a rotational cipher, but more sophisticated and lends itself to far stronger encryption, though certainly not the most robust of encryption. And so we then turn our attention to, for those interested, to the hacker edition of problem set 2. So the hacker edition, which I would encourage you not to be daunted by the fact that it's labeled hacker edition, but do read through them both. Certainly if you're among those in between, and so even if you're less comfortable, you might as well see what's out there, what might tempt you. So in this problem set edition, you'll focus still on cryptography, but on that algorithm we waved our hands at slightly, but called DES. And DES is a more secure cipher, certainly, than Caesar or Vigenère, but certainly not uncrackable by today's standards. And so the hacker edition of this problem set challenges those who take it up to crack some passwords that we have provided in encrypted form to you. And the problem set elaborates on exactly what this means, but what you'll see is that we excerpted from an imaginary and insecure computer the list of username and encrypted passwords. So we have the pointy-haired boss's username up top with his encrypted password, Kitty, Blaze, W. Brandeis, which are all allusions to popular culture, as you should notice G. Costanza is as well. S. Jobs, Tom Dixon from those well, I won't tell you where he's from, and then my own password, which is meant to be sort of the boss level at the end of the problem set for those who take this on. But what's particularly neat about the hacker edition is that we're using those students who take this up as guinea pigs of sorts. So we released this experimental version of our own architecture in the cloud, so to speak. This is a depiction of it that only appears in the hacker edition. But long story short, what we're currently running, I think for now 72 hours without a gotcha, is an architecture like this using Amazon's cloud computing infrastructure. And what this really means is that if this is us on campus here at Harvard Hall at top right, and that's little old you on your laptop somehow connected to the interwebs or the tubes, which are up here, well, Amazon is in turn connected to the internet, and this is our little cloud that we have built out our infrastructure in. So there's a perimeter firewall, which keeps bad stuff out and good stuff in. And then we have what we're calling a front-end virtual machine, which is sort of like our main server. This is the entry point for staff and students, such that when you SSH into this architecture, this week for hacker edition of problem set 2, and most likely next week for problem set 3, all of you, what you're doing is SSHing from you through the internet, through this firewall, into this front-end virtual machine, where a naive or more sophisticated algorithm then decides which of these back-end virtual machines to route you to. So you're probably generally familiar with the idea of routers on the internet, home routers, NAT, network address translation. All these technologies that most of you have in your homes these days are we using as well, so that when you connect to this machine, currently called hacker2.cs50.net, soon to be generalized as cloud.cs50.net, you're sort of randomly sent to, or more intelligently sent to, one of these back-end machines. So when you start typing commands, you're actually on this guy, or any of the machines in between. And what's neat about this, for instance, for this problem set, if we notice that the usage levels on these computers are really high, some really industrious hacker-type student is really eating up CPU cycles and RAM trying to crack Malin's password and all of the other ones in the problem set, well, we can monitor that, recognize it, and then literally by typing a few commands, a few mouse clicks, can we augment exactly how many back-end VMs there are, so that future students coming in to, say, start their problem sets on Thursday night won't find the resources already strapped by those who have started a bit earlier. And then once the problem set is done, so 7:01 p.m. on Friday night, can we sort of collapse the architecture back into just a couple of machines, which will get us through the next several days based on the when you start your problem set distributions. So what is this going to look like? Well, this is Putty, this SSH program. I've pre-configured hacker2.cs50.net. It's going to look identical in spirit to what nice.fas is, but we had a little fun with ASCII art, and we made our own little login screen. But then you have the so-called blinking prompt, which in Putty never blinks, and we can do such things as ls and cd and gcc and make and so forth. But we, the staff, have full control, full autonomy over this. So this is exciting stuff. And even if you're thinking we're kind of geeking out here, we're going to be able to do some neat things, as the problem set alludes to. So more on that to come. So our walkthrough. So those of you tackling still problem set 2 for the first time, maybe didn't start it at 7:01 p.m., as I know from our logs that some of you did. The walkthrough from Cato is tonight, 6 p.m., Northwest Science B101. It's this really nice building just across the street from Maxwell Dworkin, the CS building. And this, too, will be an opportunity really to be helped starting the problem set. Where do you begin? What do you do? What should you be thinking about so that you have sort of a framework with which to tackle it on your own? These will, in general, focus on the standard editions, because that is by far where the biggest draw is. Office hours, see the website, and 2 last notes. So we have gotten dozens of emails in just the past few weeks, which is wonderful. There's plenty of us to field them, but it does tend to get a little overwhelming. And also, when we answer questions, certainly you who have not emailed us don't necessarily see the response. So we have launched, as planned, the course's Bulletin Board, which to get into, click the Bulletin Board link, log in. I'm logging in with a fake student account right now. You can now log in with your FAS account or your cloud account when you get it. This will then lead me to what we hope you'll find to be a fairly simple bulletin board. So in here will we post announcements. In here will we post other random things. And then we'll have dedicated bulletin boards for each of the problem sets. So if you've not tuned in just yet, and that's fine if you haven't, because this literally debuted Saturday afternoon or so, you'll see, for instance, those, it correlates. There's more posts already in the hacker edition of the problem set. But what you'll see is, say, long and interesting discussions about stuff that's come up on that edition. So turn here for questions, turn here for answers, and then if you need to, turn to email so that more than just you can benefit, hopefully, from the kinds of data, answers we give back. And lastly, let me address this, since I was the one who counseled you to use this website. We've recommended last year in this cppreference.com, which is c++reference.com. But as you know, there was the C++ half and a C half of it. Unfortunately, in the recent months, have they pretty much made everything look like C++. So you'll see in particular when you do sharp includes on the website, it says something like sharp include bracket C math. Like C-M-A-T-H close bracket instead of math.h. Well, these kinds of things are going to be unnecessarily complicated. So what we did was on the course's resources page, the link is just called C reference. We also simplified it to draw your attention only to what we think are the best resources, or I do at least. And we've ripped out all the C++ stuff and fixed any of those inconsistencies so that you don't run into any problems. And if you've never seen this, the means by which we literally rolled back time was thanks to the Wayback Machine. If you've never seen such a thing, this is another, so sort of, you've all probably Googled yourself before, right? So if you ever want to Google yourself like a year ago or 5 years ago and see what someone's homepage looked like, God forbid my own, and even other websites back there, you can, for instance, go back to, I'm not going to go there. So you can go back to, say, friends, personal websites, or other places. And this website has essentially been trolling the interwebs over the years, archiving websites. So we went into those archives and pulled the old copy of the website and then tweaked it. So any questions about that or anything else? All right, so let's get to that part of the course where we teach you to think more carefully and effectively. So this was the algorithm with which we began, week 0. We all sort of awkwardly stood up. You said hello to a couple of people next to you. And then we counted each other. And it worked out pretty well. It was a little slow. But what was compelling about that algorithm, that procedure and spirit, was what? Like what motivated, besides a little drama in week 0, using that algorithm as opposed to the more naive grade school approach? So it's faster. Why? Yeah, so you have fewer steps than going 1, 2, 3, 4, because we're leveraging each of you individual machines, computers, brains, because we've sort of given you all the same algorithm. We told you to execute it. And what was particularly compelling about this algorithm was what happened at the end of each round or iteration. What's that? Yeah, so you ended up with a lower number. In particular, half of you guys sat down, assuming the algorithm was being executed correctly. And that's pretty compelling, because in one iteration of mine, it was like 1 of you was sitting down, and then 2 of you, and then 3 of you. Whereas when we all did it together, it was like 100 of you sitting down, and then 50 of you sitting down. And we were taking much larger bites out of the problem. And we described that as logarithmic running time. And this is where we'll slap some formal labels on it, but none of it too scary. So this was a quick and dirty chart that I whipped up with Excel, just with some sample values. And all this thing is telling us is the following. So on the x-axis here, called n, I'm sort of generalizing the notion of the size of some problem. In this case, the number of students in the room. And on the left-hand side, I've got t of n. So it's like a functional notation. So t of n is the running time required to deal with an input of size n. And I just sort of arbitrarily chose some values here based on some functions I want to draw. So what is this saying? Well, this is saying that if I have, say, 20 students in the room, right here, n equals 20, what's the running time of, say, my grade school, my linear counting algorithm going to be? Linear in the sense that I'm sort of walking down the line counting people. Well, if you go all the way up, it's 20. And that's kind of intuitive, if not self-explanatory. But what if I did something more clever? Well, if we took this logarithmic approach, which is denoted here by these circles, which is this line here at the very bottom, it certainly has a very different shape. And what it's telling us is that if we have the same 20 students in the room, but we use that fancier divide and conquer algorithm, it takes us just 4 iterations. Now, granted, this is kind of glossing over some details, right? Because in your directions, it's not like one toll of the finger. There's actually a few things happening. But if we at least sort of compartmentalize that iteration as just one big step, maybe it's a slightly bigger step than mine, but conceptually, it's one step, and then we compare our steps together, well, then this algorithm would appear to take much less time. But notice where it gets compelling, right? We can't even fit, say, 100 students on the screen. But if I extrapolated, it would be what? Well, literally up at 100, somewhere closer to the ceiling. For the linear algorithm, represented as n. But again, this was compelling because with 100 students, it takes just 6, maybe 7 such iterations. And that's pretty powerful. Well, what does this mean in real terms? Well, these were some scary numbers we put up at first. But it was just to give a sense of the magnitude of these things. So in this column on the left-hand side is n. So if we've got n equals, say, 16 students in the room, and we use the naive counting, the linear approach, it's going to take 16 steps. By contrast, if we use the logarithmic approach, the parallel processing one, or divide and conquer, describe it as you see fit, it takes just 4 steps. But it gets really compelling again. If we actually sort of overflow Sanders, have 1 million students in CS50, well, it's still only going to take us 20 such steps. And that's where sort of the magic, or really what's, I think, particularly compelling lies. Well, what does this really look like? Well, these are some excerpts from like an old data structure books that I just scanned just to make a point. So this shows us those same functions, but just graphed. And the numbers here don't really matter. It's the shapes of these lines that are interesting for now. So on the x-axis here, again, we have n. And n is only going from like 0 to 10. So this is a pretty small chart. And then then t of n is going from like 0 to 60. And what's interesting to note is things like this. Well, here's n, if you can see there. So that's n, and it is, in fact, a straight line. Log of n doesn't look all that much better there, but it feels like it has a different curve. But if we scroll up here, let's look at this thing, exponential. So anytime you see 2 to the n or some constant raised to a variable, that's generally bad in computer science when it comes to implementing algorithms or code. And those of you who maybe took a fairly simple approach, like even we did, the staff, with our solution to the optimal change-making problem, we pretty much just tried all possible solutions. So if you feed our sample solution really big inputs, you're going to be waiting there a really long time for the possible answers. And that's because that brute force approach is essentially described as something exponential. And what's, again, sort of the takeaway here is just the ridiculously large gap, even for small inputs, when you're talking an algorithm that's linear or even logarithmic versus exponential. And these other things, if they're too small to see, this is n squared and this is n cubed. But the picture gets a little more interesting if we sort of zoom out and we give ourselves a bigger x-axis and a bigger y-axis. You really get to see what happens sort of in the long run, so to speak. So this is the same kind of graph, but we've just doubled how many numbers we're fitting on the x-axis. And as a result, we need to enlarge the y-axis so that we can see things. And it's starting to get a little ridiculous. So down here is n, which is one of these straight lines. And then up here is 2 to the n. So apparently, if you have an input of just size 14, well, in n, it's going to take you, what, 14 steps. But if you've done something stupid or something necessary that's exponential, it's going to take you 10,000 steps. And if we take this one step further, in the long run, all of these things essentially look the same. Whether you've got an algorithm that's linear or quadratic, that is n squared or n cubed, it's when you start talking about different orders of magnitude, so to speak, where the variable goes from the base to the exponent, that things get really scary and really slow. And this is sort of the type of code, certainly, that you want to avoid. But the curious thing, and the kinds of things you'll explore in courses like CS121, CS124, if you take those courses after this one, is what kinds of algorithms either necessitate algorithms that do run, dare say, as slow as that, or are there actually more clever things you can do? Those courses are theory courses and data course, respectively. So let's see if we can't describe this kind of stuff a little more formally so that moving forward, you can sort of look at your own code and say, well, this is good because not only does it spit out the right answers based on some random tests that I've been running tonight, but you can also point to, well, look at this loop, look at these conditions, this is going to execute in this situation. You know, the running time of my code is n squared. The running time of whatever algorithm I've implemented is such and such. Well, what labels can we slap on this? Well, henceforth, if you ever want to talk about the worst case running time for your code, like give me the worst possible inputs, like only pennies, for instance, or pennies and quarters, and leaving out some really crucial denominations. If you give me a bad situation like that, well, you can describe the worst case running time of your algorithm with this symbol we know as big O. It's just a capital O. And then parenthetically after that will be described with function notation just how many steps some algorithm takes. The counterpart to that on the lower bound is this omega symbol, capital Omega. So if you want to say my algorithm in the best case is such and such, you say it's in omega of such and such. And this way, sort of mathematicians and computer scientists will know what you're talking about. Now this thing here, you kind of guess based on the picture, what's it mean probably? So it's not actually average per se, but it's the coincidence of both upper and lower bounds. So if it's both worst case something and best case something, you can say that it's theta of something. But you'll find that the lower and upper bounds are generally more common, certainly at this point in one's computer science career. And if you really want to be sort of, if you understood that, great. Now try to understand the formal definition. And many of you, I'm sure, will at first glance, but we offer it just to formalize this, what we'll use today, as just more of an intuitive idea. Upper bound to lower bound, and then one in the same. But there's the formal mathematical definition, which will make even more sense, I think, when you actually have actual code or algorithms to look at. So here, just some more jargon so that if I start using it and don't assume it, you have a little cheat sheet. So we've already said that something that runs in linear time, like my naive 1, 2, 3, 4, 5 counting algorithm, is linear, aka big O of n. Because in the worst case, how many steps is it going to take me to count n students? Well, it's kind of an obvious answer, n steps. But it's not always going to be obvious because if the inputs actually vary in some situations, can you come up with different answers? Constant time, so rather than say this takes 2 steps, this takes 3 steps, or this takes 4 steps, and then say this is O of 3 or O of 4, the world just simplifies and says if something takes the same amount of time, the whole, every time, it's big O of 1. So even if it's a contrived example, give me an algorithm in a sentence or less that runs in constant time. Yeah. OK, taking the first element from a list. Perfect. How about even something more real world? Hello world. No matter how many times I say it, it takes me just one sort of breath, one step. Hello. Hello. That algorithm, that printf, just requires constant time, big O of 1. Good. So logarithmic is this thing, linear is this thing. You don't usually hear people say superlinear. You'll just hear them say n log n. Quadratic's popular, polynomial's popular, all of the rest are popular. And they're listed in order of increasing badness. So if you have an algorithm that's factorial, which is actually, you can come up with contrived examples, it's generally a bad thing. And there's also some more formal problems in computer science and even the real world that approach this kind of running time. And n factorial pretty much means that if you've got a problem of size n, like n people, or n cities that you want to visit, and you're asked a question like, how can you minimize the amount of gas you use to visit all n of these cities? Or how can you minimize the number of miles you physically need to cover in order to touch all of these cities? It's generally known as the traveling salesman problem. Well, sort of in the worst case, the one reliable way of answering that question, what path should you follow? What city to city? Well, you could kind of consider all possible sequences of cities. So Atlanta, Boston, Chicago, Atlanta, Chicago, Boston, and so forth. Those kinds of permutations. And how many such permutations are there? n factorial. It's bad if you have to check all possible ones, even for relatively small inputs like 20 cities or 30 cities. So kind of real world interesting outgrowths of these questions. But let's start with something that we can sort of frame more simply. For this, I need a brave, non-talking volunteer. Well, you can talk, but you're not expected to. Yes, come on down. What's your name? John? All right. Oh, OK, John. Yep. OK. All right, so sort of game show style, we've prefabbed a demo here. All right. So John or John? Sean. Sean. OK, Sean. Nice to meet you. All right. So you do have to sign a little legal form after this, if that's OK. But we'll get to that. OK, so your task here, Sean, is the following. I have hidden behind these doors the number 7. But tucked away in some of these doors as well are other non-negative numbers. And your goal is to think of this top row of numbers as just an array, or just a sequence of pieces of paper with numbers behind them. And your goal is, only using the top array here, find me the number 7. And we are then going to critique how you go about doing it. All right. Find us the number 7, please. No. 5, 19, 13. It's not a trick question. 1. At this point, your score is not very good, so you might as well keep going. 3. Go on. Frankly, I can't help but wonder what you're even thinking about. So only the top row. So you got 3 left. So find me 7. $17. OK, good. You're off the hook for a moment, but bear with me if you could. All right, someone gently describe the algorithm that Sean used to find us the number 7, thinking of this as an array of numbers. Exponential? OK. Yeah? Yeah, so it was pretty much linear. He started at the left and moved to the right. He did skip the second to last one, so maybe that's a little condition in the algorithm. But for the most part, it's linear. So in the worst case, well, in the real case, how many steps did it take Sean here? OK, so n, or maybe n minus 1, because you did skip that one. But that's fine, slight optimization. But n. And in the worst case generally, if all I told Sean was that you've got an array of non-negative numbers from left to right, and you've got 8 of them, in the worst general case, what should be the running time of that algorithm? N, right? In the worst case, some jerk's going to put the thing you're looking for at the end of the array. So the question now, if you'll bear with me for one more demo, what's a possible optimization here? Like, wouldn't it be nice if we could make certain assumptions, perhaps? Like, what could help us out? OK, good. So what if I told Sean he's allowed to assume something about the numbers? Not just that they're non-negative, which really doesn't help him. They're still just numbers hidden behind doors. But what if I tell you that they're sorted, or they're monotonically increasing, or they're still non-negative numbers, but they go from small numbers to large numbers? How would that affect your algorithm if you can now use our second array, which I have had just the foresight to lay out in that order? Still look for 7, please. 11, 5, and 7, if we could. Now, do you mind if we turn this into a speaking role? OK. So and I'm going to stand close to you so we're both mic'd. What was your algorithm if you had one there?
All right. Well, knowing that knowing that they're increasing, just to, I guess, sort of narrow down my search area. OK. By finding which regions contain sort of the right set of values. OK, and you chose, I think, this one first. Why? Yeah.
OK, so close to the middle. And then what'd you do when you found there to be under this door 11?
I knew it was on that side, so I checked the middle of that side.
Exactly. So you sort of divided the problem, if we come full circle here, into something half as big, and then chose something in the middle, or you kind of have to round low or high, and you went high, 5, but now you know it's not here or to the left. You know it's not here to the right, and so you've immediately narrowed down the possibilities to this guy. And so with this algorithm, in the real terms, this was running time of 3 steps. But if we generalize now, what's the running time of this more clever algorithm? So it is, again, log n, because it's pretty much the same thing as the phone book. Instead of 1,000 pieces of paper that I split in the middle, in the middle, in the middle, we had 8 pieces of paper that you did effectively split in the middle, in the middle. And you know, it would be more clear that we're dividing in half, even though we have these rounding errors, if we had more pieces of paper. But it's the same algorithm. So this has been either wonderfully memorable or wonderfully awkward. So maybe one final round of applause for Sean. And we have a nice little parting gift for you here. OK, so what's the takeaway? Well, let's slap some labels on here. This first approach is what we'd call linear search. It's a linear algorithm. What's compelling about that first algorithm? Sort of fun as that first demo was, tell me something that was actually good, that was smart about Sean's first approach of left to right. Yeah. You don't miss anything, right? It's sort of bound, except for this little hiccup here, right, bug, it's bound to be correct because it will eventually find the number. It might take a while, it might take n steps, but it will work. And so that sort of speaks to correctness. It's a simple algorithm. I mean, how many lines of code would it take to write something like that? It's 2, 3, right? You got like a for loop or something, and then you've got maybe an if condition there, and then you've got a printf or a return value, something like that. So these are the kinds of terms you should start thinking, because one of the resources that you have available to you is not only the number of CPU cycles that a computer has, or the amount of RAM or disk space, but frankly, another real-world constraint is the programmer's time, your time, the mental difficulty, the time required to actually code a program. And so sometimes it's absolutely compelling to do the quickest, the dirtiest, so to speak, implementation, because if it gets the job done and it takes less time to code it, plus if it takes less time to code it the simple way, plus run it, than it would to spend hours doing the most sophisticated algorithm possible that's theoretically as fast as possible, but then it takes just a second to run, but it took you way longer to implement, probably not a smart idea. And I mean, I can even speak to personal experience, like in grad school. We used to run a lot of simulations, and long story short, my research was on internet worms and detecting them on Windows platforms with new techniques. And we used to take in log files from various friend systems who had consented to running my sort of prototype software on, and we would try to analyze gigabytes of software, or gigabytes of log files, just looking for patterns, really, patterns that worms might manifest. And there was this trade-off. I could either spend all night or all day sort of coding the best possible algorithm so that it would run like this, or frankly, given a world of, a world of constraints, like my free time and such, sometimes I would take the quickest, the dirtiest approach, and then just go to sleep for 8 hours and let it run for 8 hours, because when I wake up, then it's done. So this isn't to say that's sort of an acceptable trade-off come problem set time, since we are trying to convey sort of lessons that can stay with you, and procrastination and shirking is not so much one of them. But that is to say that your own time and the complexity of a program is itself a resource, or a metric to consider. So how might we express that same algorithm of Sean's in pseudocode, English-like syntax? Well, this week we don't really care so much about the language, so let's do it like this. On input n, for each element, call it I. If I equals n, go ahead and return true. And then it's not else return false, but when do I return false? Based on the indentation, it would seem. Right, only return false if you get all the way to the end of the program. That is, you finish that loop, not having found n by iterating over all possible values, then do you return false. So the indentation in pseudocode, important here. Well, what if we wanted to implement now Sean's more clever approach with the second array? So given the assumption that the array is sorted, this gives us some flexibility because now we can be more clever, but the obvious pushback is it already kind of looks more complicated. Now, that's not to say this is not a goal one should seek out, implementing it better, but again, it's to sort of point out that you rarely get in computer science and programming anything for free. So if you want a better performing algorithm, you're going to have to put out something for it, and probably an investment of time or more mental energy. But the algorithm itself is not that hard, right? It's start in the middle, look at the element, go left or go right, repeat. It's just when it comes time to code it that you have to think about those so-called corner cases. Like when Sean went for the middle, kind of a problem when there's nothing in the middle per se. So he kind of had to arbitrarily go left or right. But the gotcha there, at least that should come to mind, is what if you're not consistent? Or what if you're always going left? Does that mean you're potentially going to miss some element? Because if you are, your algorithm is certainly no longer correct. So we won't dwell so much on this particular pseudocode, because I think it'll get a little dry sort of walking through it line by line. But what we tried to make clear here was with various familiar constructs, like a while loop here, these let lines is just like a pseudocode way of saying declare this variable called x, or called first, and initialize it to 0. Well, here's a loop. Here's another variable declaration. Here's a condition. And this algorithm ultimately, given an array whose elements, like last week, we'll describe as the array's name, bracket 0, up through n minus 1, and k in this case, which is the number I care about that I'm trying to find. Well, ultimately, I'm doing things like, I want to try to find this particular value. And what these several lines have the effect of doing is grab the middle, then go check it, then go left or go right, and then repeat. And the repetition comes in from the while loop there. But there's this neat thing that we can introduce today. And it's this concept known as recursion. And it's a sort of an approach, a technique when it comes to writing programs that will actually simplify what I'd argue is, not a hard algorithm to code up, but not sort of straightforward. Like even I would sort of have to think through these lines again and again to figure out, OK, am I missing, in fact, any corner cases? Well, let's see if we can't do a little better in principle. So here's a simple little program I wrote that does what based on the comments in the code? It's just what? It's called sigma. That's kind of the first clue. Return the sum of 1 through m. So if you remember any sort of mathematical notation, this is like saying give me the sum of I from I equals 1 to m. That's the fancy way of saying sum up all the numbers from 1 to m, or 0 to m. It's the same thing. So what does this code do? Well, in this line here, I have int sum equals 0. Let's go ahead and pull this up actually in actual code. So I'm going to connect to Putty. I'm going to go to nice.fast. I'm going to go log in as CS50. But soon we'll eventually be moving all of ourselves over to cs50.net. Let me go to the lectures. OK, and we've got sigma 1 here. OK, so this is the same program here. But let's notice first what I'm doing. So int n. I moved something. What do I do here? M. There we go. So I've got the sigma function here. So if m is less than 1, return 0. Why am I doing that? What's going to happen if I don't have that check? Oh, it's an infinite loop, but what does that mean? Like, why does that get induced? Well, if m is less than 1, but my loop is apparently going the other direction, but starting at what? 1, that's sort of a bad thing since I'm going to be checking for a range that I never actually hit. So let's go ahead and run this program first, just as a proof of concept. So let me go ahead and quit this. So I'm going to do make sigma 1. All right, compiles OK. I'm going to run sigma 1. And let's do some cases I know the answers to, like 2. Whoops. Doesn't take command line arguments. Let's give it 1 here at the prompt. 2. All right, so that makes sense, right? 0 plus 1 plus 2, 3. All right, let's do one more. Let's give it 3. So that should be 6. Maybe at this point, it's kind of an interesting problem set takeaway. Maybe it's time to call it quits here. But again, to this point of corner cases, when you're testing your own code in problem sets, you should absolutely be testing things like foo to make sure it catches that. You should be testing things like 0, which is a little worrisome. How about negative 100? similarly worrisome. So sometimes in problem sets we'll tell you, you may make this assumption. Like in the ISBN problem, just assume we're only going to give you 10-digit values because otherwise you run into nuisances in the first problem set that we didn't want you to deal with. But in general, if not otherwise told you can assume anything, you should assume nothing. And you should assume that we, the teaching staff, are going to try our best to break your code and find those corner cases because it's that sort of maybe fear that will perhaps drive you to write yourself more robust code. And again, this is compelling because anytime you yourselves have been running iTunes or any normal application on your computer and it crashes or starts hanging, well, that's because someone made a mistake. And so clearly there's motivation out there to writing better code since it does affect real people. Now, how does this thing work? Let's look at the main routine first now. So notice I'm using CS50's library, standard I/O. That's pretty typical. What's the deal with this prototype? I seem to be defining the sigma function without actually getting around to defining it. Why? So that's this top line labeled prototype, the function prototype. Yeah, so if you want to call a function, but you've defined that function later in the file, annoying though it is, C does not ever look ahead in your code to see, oh, maybe it's coming up later in the file. You have to proactively tell C, by way of these function prototypes, what functions are in fact defined in this file, and sometimes we'll see even in other files altogether. So notice what I've literally done, if we scroll forward to the sigma function, is notice its signature. The signature of a function is a statement as to what kinds of arguments it takes and in what order they appear. Well, I noticed that I've pretty much just copied this. So it returns an int, the function's called sigma, and it takes an int. So I scrolled up to the top of this file, and I simply described it as int sigma int. And notice I haven't done one thing here. What's missing that wasn't missing down below? Yeah, so the name of the variable. Turns out it doesn't matter. Because C doesn't care so much about what the names of variables are, but rather their order when it's trying to look for a matching function, all you need to provide, and this is really a stylistic decision, is the minimal amount of information for it to find the function. And that's literally what you're telling the compiler. You're saying, here's a signature for a function that you should expect later. And so by seeing this in advance, can the compiler say, oh, if I see sigma down in the main function, that's fine. I'm going to compile it and assume that it exists because the programmer has proactively told me I'll see it eventually. So nuisance, but necessary. All right, what if we scroll down to the main routine? So here's this sort of common use of do while. Anytime you're trying to take user input, but you want to pester the user to make sure that they give you what you expect of them by prompting them once and then repeating if necessary. So apparently I'm asking the user for a positive integer, please. I'm getting getInt. But here's another interesting point we can bring up. Why did I, even though it looks a little weird, declare the int outside of this for loop instead of doing this sort of more popular or maybe more intuitive approach there? Yes, well, so it effectively gets declared again and again, but more damningly than that is anytime you declare a variable, it only exists within a given scope. So notice I'm hitting a keystroke here that's toggling my cursor between the curly braces. The sort of rule of thumb is that variable defined inside these curly braces will only exist inside those curly braces. Now that's kind of problematic if I want to use n where? Outside of them, i.e. down here. So that was sort of a necessary thing to do. Let's see what else is interesting here. So while n equals 1, that handles the positivity. Now notice here I'm sort of punting. So whereas in week 1, week 2, we might have just put all of the code right here. Now we're trying to preach this principle of hierarchical decomposition. That is, factor out chunks of code that sort of make sense intuitively, that conceptually sort of do one thing that you can describe with, say, an English sentence, like compute the sum of some numbers, and factor it out to a function so that you define your own function down below. And functions, again, by nature, can take inputs and can return output, aka return values. So sigma, I decided would take an int, return an int. Now how do I compute it? Well, it's just a simple for loop. Right? There's no magic here. This is the kind of code we would have written a week or two ago. But I did do this one check, which is kind of interesting. In fact, let's see if we can't break our code. So let's forget about this corner case or this malicious case, as the case may be. Make sigma 1. Still compiles OK. Sigma 1. And let's run it on 3. Still 6. Let's run it on 2. Still 3. Let's run it on 0. Still OK. Let's run it on -1. Didn't seem to break anything. What's going on? Yeah, so we had this sort of extra safety net up here, which in this case is arguably redundant. But now that I've started to write my functions outside of main in such a way that they're reusable, maybe by me elsewhere or by other programmers altogether, not necessarily a bad thing to make sure every function sort of protects itself. Remember Sterling, we had that very quick example last week where if you pass Sterling, what value? It segfaults, it blows up. If you pass Sterling, that function for computing the length of a string, if you pass it null, bad things happen because for performance reasons, years ago, the designers of C or the compiler decided, you know what, let's not bother checking for null because if the common case, if 99% of the time the user passes me a legitimate string, well, I'm just wasting CPU cycles by checking, is the string equal to null? If so, return. If not, count the characters. And just for those 1% of stupid users am I actually checking again and again and again the value of that pointer. It's kind of a performance trade-off. So the burden instead was pushed back onto the caller, the person like us using the function, for what's arguably a reasonable reason, so long as it's documented as such. But let's break this thing further so that we can actually tie together part of last week's discussion. So here, I'm just going to do this, whereby I'm just going to let getInt get me an int, and I'm not going to worry about negativity. Let's recompile that, rerun sigma. Let's do 3, still works. 2, still works. How about 0? Still works. -1. OK. -10. OK, we OK? Oops. Why is this still working? Well, let's see. So we're passing in, say, -100. So is I less than, let's see. So I starts at 1. I do this loop so long as I is less than -100. Does that ever happen? No. So still, we sort of have this other redundancy check built in. OK, so that's not such a bad program. Let me rewind all my changes so that we don't post the wrong thing. But let's take a look now at this version. That was a good thing. So we have a bunch of error checking there. But can we implement this thing differently? So now this is the implementation that uses a loop, that uses iteration, to just count up the numbers from 1 to m. Well, let's see if we can't make this more clear. So what about this approach, which is literally 4 lines of code and 2 comments? What does it do? So this is kind of neat, because what does it mean to count the numbers from 1 through m? Well, it's kind of, if I want to sort of make a circular argument, it's kind of like computing the sum from 1 to m-1 and then adding 1. Well, what's the sum of 1 to m-1? Well, let's again sort of cheat and just push the problem back on me. Well, it's the same as computing 1 plus all the numbers through m-2 plus m-1. In other words, you can sort of bite off one piece of the problem and then just say, all right, just repeat that algorithm on the smaller piece. Right? So if, again, the problem is count all the numbers from 1 to m, well, that's the same as saying count all the numbers from 1 to m-1, give me that answer, and I'll just tack on the additional m and get the same result. Well, it turns out you can sort of borrow this idea whereby you have this circular, or aka recursive definition of the thing you're trying to compute, and you can capture it in code, and code that is arguably, if not a little bit more amazing, certainly simpler to look at. So notice here, here's the same function called sigma, still takes an int m, but I have this thing called the base case, which again is my safety valve. Like in case the user tries to mess with me, I'm going to return 0 by default, arbitrarily, if they try to pass me anything other than a non-negative, or anything other than a positive number. But what about this? It seems that we can literally boil down what took this many lines of code, which clear but not elegant perhaps, into really just one magical line. So what does it mean to compute the sum of 1 to m? Well, just like I said, it means compute the sum of m1 to m-1 and then tack on m. Well, why does this work conceptually? Well, let's see. So if I have m equals, let's say, 2. So I call this version of sigma when m equals 2. So I first check the base case. Is 2 less than or equal to 0? Well, no. So that doesn't execute. So what do? I'm going to return, what am I going to return? 2 plus sigma of 1. All right, so what's sigma of 1? All right, so 1 is not less than or equal to 0, so my base case doesn't apply. So I'm going to compute what? 1. So I'm going to return 1 plus sigma of what? 0. OK, so again, here's the sort of circularity. I just keep punting back to myself to recall the same function, but with a smaller input. So now I call sigma on 0. So 0 is certainly less than or equal to 0. And so this guy returns 0. So immediately, m equals 0 returns 0. So what's going on? Well, now notice we have this mapping. So what's the answer to sigma of 0? It's apparently 0. Well, that means the answer to sigma of 1 is 1 plus 0, aka 1. But I need that answer here because what's the answer to sigma of 1? Well, that was, let's see, 1 plus 0 is 1. So that means the answer for sigma of 2 is 2 plus 1, or 3. So it's kind of, frankly, this really neat feature just of logic that you can take some problem, sort of bite off one of its elements, and solve that same problem again and again by just tacking on the thing you bit off at the end. Now, in this case, does it solve the problem any more correctly? No, odds are, unless I made some typo, the program's going to work exactly the same. Well, what about running time? Let's go to that. So does this program take more time or less time to run? So I heard less time, but I also heard some more time. Someone who said more time. Why? So that's pretty astute. So recall our picture last week when we said anytime you call a function, what happens in memory? Well, one of those stack frames gets tossed onto the stack. That is, the operating system says, damn, I need like another 32 bits of memory, maybe more. Let me reserve that for the user, hand it back to their program so that they can start using it. And then as soon as that function's done calling, I'm just going to tear it back down. So intuitively, there's some work to be done anytime you call a function. And that is, in fact, true. So generally, at least when you're starting to write very low-level, high-performing code, calling functions does have a computational cost that comes with it. That's not to say we at this point should worry about that, but it is a valid point here. Why is this maybe, let's see, you said it was slower. Who said it might be faster? Why is it arguably faster? OK, you did, but you're not sure. Well, I'll hypothesize, just sort of off the cuff. Well, it looks like there's more lines of code here. There's more stuff going on, at least explicitly in this program. So maybe if you add up all of the low-level machine instructions required to do this kind of code versus this kind of code, maybe it is, in fact, faster, this recursive version. So only really by benchmarking this, by running it and testing it, could we really get a definitive sense, because it depends on so many variables: the operating system, the hardware, and the compiler itself. Yeah? Oh, clever. OK, so let's come to that. But OK, so yeah, so verbally, let's do that. So it turns out there is a third version of this code that we can write. Because if you ever have the summation from 0 on up to some value, it turns out you can generalize the sum without even having to count manually as what? Yeah, so this is sort of, if you remember like at the back of your math books or physics books in high school, there was that like cheat sheet of formulas. Well, that was one of them. If you have big sigma of this, this actually sums up to this, or m squared plus m over 2. So in fact, if you hard-coded that into your program, you've just one-upped all of us. Because then your running time is not, what's the running time of this first one? It's n, right? It's linear. It's literally looping from left to right, small to large. While this one here, it's maybe less obvious, but how many times is sigma getting called? Pretty much n. Maybe n minus 1 if we count carefully, but pretty much n. So this is still linear, even though it's calling functions again and again. But if we take this approach, where we literally hard code this with an arithmetic expression, which we know from week 0 or week 1, pretty easy to do in C, right? Int answer equals m times m, or m m plus 1 all divided by 2. What does it take to compute that? That's just one step, right? Maybe one big step, but just like we can sort of clump some logically related steps together, reasonably so, as we did with the counting, that too would be even better. So then what's the answer to the who cares question here? Why even introduce something that might be slower because of all the additional function calls, it is not clearly better than the best possible algorithm, so who cares? Why is this maybe an attractive thing to bear in mind, a neat trick, a useful tool? Yeah? So that's true. There's not always going to be that little cheat sheet at the back of the math book that gives you a formula with which to solve it. Maybe it exists. Maybe you don't know it. So that's certainly reasonable there. But what about this version versus this one? Like, what do you like? If you've sort of wrapped your mind around why this thing even works in the first place, what do you like about it? It's less code, right? And if you're starting to sort of come to our side, there's sort of there's a certain beauty to something like this. There's a certain elegance to code like this vis-a-vis something like this, which is more deliberate, like maybe more clear. But just look, you can sort of boil this program down into one interesting line of code. But there is a gotcha. So we tried to break our previous version, Sigma 1. What if I go into Sigma 2 here? Well, let's first make it to do a sanity check that it works out of the box. So Sigma 2. I'm going to run it with, let's see, 3, that works. With 2, that works. 10, that works. Will it break at some point? How do I break it? Yeah, so what if I do something really, what just happened? Not that funny. What just happened? So this is Sigma 2. Something bad just happened. This is the sigma function that's getting called again and again. Why did it segfault? So yeah, maybe ran out of memory because specifically what was probably happening. Turns out I came prepared with a picture. Right? So think of foo now. This was the picture from last week. Think of foo, not as foo, but sigma. What's happening every time sigma is called? Another frame, another frame, another frame, another frame, another frame. This can't go on forever because there is an upper limit, whether it's 2 gigs or something smaller. Because in fact, up there too, eventually, is that thing called the heap, which we'll start talking about before long. And there's also the so-called text segment of your program. When you double-click an icon on your computer and you run a program, that program's got to get loaded into memory. Where does it end up? Well, conceptually, it ends up at the top of this rectangle, the text segment. The zeros and ones that represent the executable are up there too. And if the operating system's written right, it's not going to let you clobber the actual program code with these stacks. It's going to detect that there's been some kind of overflow of your segments, so to speak. So just to prove that that wasn't a fluke, let's do this again with like a lot of zeros. Yeah, segmentation fault, core dumped. In fact, let's do a little proof of concept here. In addition to returning a value, I'm going to put in braces here so I can do 2 things. I'm going to say print, let's say a print f, %d, and then comma m. Let's just print out the current value of m just to see that something is in fact happening that's perhaps useful. Sigma, let's give it a really big number. So far, so good, huh? Oh, there we go. So we only got through a couple 100,000 frames on the stack before we exceeded our limit. So there's apparently this gotcha, right? Nothing comes for free. So yeah, you want to write more elegant code. You want to solve the problem in a manner that's more consistent with your thinking. Well, you're going to have to potentially pay for it by either your program not being as correct as it was before because of physical limitations. But it turns out, just as an aside and sort of a teaser for higher level courses, there's no reason that a smart compiler can't realize that the very last thing this program does is what? Call itself, right? It returns a value, yes, but it makes a recursive call to itself. And if that's the very last thing this function does, it doesn't really need its own stack frame for very long, right? Because there's nothing else that's going to be using variables from the stack frame. So this is what's known as a tail recursive call. If a function's very last line of code is a call to itself, well, a smart compiler, if you turn on optimizations like GCC, should be able to realize, oh, this is tail recursive. That is, nothing is going to happen after this call. Therefore, why in the world would I pile up all of this information, all of this memory that I've reserved for this function? Because the moment he returns, does he need them anymore? Apparently not, if this is the last thing he's doing, is calling himself. So you can sort of trust in the intelligence of your compiler if you run it with certain switches to at least mitigate that particular concern. So kind of neat stuff. Well, what about recursive implementation of that other approach? So the approach Sean took earlier, we coded up and waved our hands at the pseudocode for what was a binary search algorithm, so to speak, divide and conquer, but it was iterative. There was a loop in that code. Well, it's a little easier, I would say, to think about something that conceptually is recursive, right? Go to the middle, go left or right. Repeat, repeat, repeat. Anytime you have that kind of repetition, particularly when the problem is getting smaller and smaller, you should sort of think, candidate for recursion. And you shouldn't be discouraged just by the fact that you can't handle relatively large inputs. There are other solutions for that. So let's just think through this one without worrying so much about the math, but more the spirit for now. So on input of given an array, and also the first and last and k. So what's the deal here? Well, in C, especially if you guys are coming from the world of Java, when you get an array, there's no easy way or no reliable way, let's say today, to figure out what the length of that array is. You yourself have to remember it. If you declared an array, you better remember how big it is. If you're handed an array from some other function, that function better tell you how big that array is. And so here in my pseudocode, I'm assuming that I'm getting past an array, but also, just because I thought it would help me, a pointer, so to speak, the index value of the first element that I care about in the array, and my other finger is going to conceptually go on the last element. Because the idea is going to be start like this, go for the middle, then go here, then move right, and sort of move your fingers iteratively, one jump at a time, until you hone in on the one and only element, hopefully. So how does this work? Well, if first is greater than last, why do I return false? So if first, left hand, is greater than last, that really means this situation has happened. Why is that worthy of returning false right away? Right? Like I've not found it. If I've sort of been narrowing in on the problem and then I go right past the answer, well, it wasn't there, assuming my code is correct. So we return false because the thing's not found there. Otherwise, let's compute the middle element and worry not so much today about the rounding issue. But else if k, the value I'm looking at, is less than what's at the middle element of the array, what do I want to do? Just in English. If the thing I'm looking for is smaller than what's in the middle, which direction do I go? Yeah, I sort of repeat this process on the left-hand side. So if this function I'm implementing, we'll call it recurse, just to generalize, well, then I want to return myself, but passing myself the same array, because it's just one big chunk of memory, pass in the first, my left hand, because it still might be to the left, but now let's pass in middle minus 1. So if this was the middle here, so here's first and last, here's now middle, I only need to now search at first through middle minus 1. And so we pass in the smaller range of values. Otherwise, if it was to the right, I instead go from middle plus 1 up to the last element. And even though there's a lot of English words here because it's in pseudocode, this arguably has much more of an elegance to it than the iterative approach. And I mean, there is, again, if you can start to see it, or if we can win you over intellectually, there's sort of a beauty to these solutions that are recursive because they just make sense and they're quite clean to code as well. In fact, later in the course and in other courses, when you get to discussions of trees and graphs, things like the traveling salesman, anytime you have all these different nodes connected together, even things like Facebook, frankly, when you're doing the 6 degrees of separation type computations, well, recursion is often called for in graph context because it means you can sort of start at a node and then just keep searching and searching and searching by executing the same code again and again, but passing in a different starting point, say one of the child nodes or one of the neighbors, one of the friends. But there's a problem here. So we've gone from something linear and correct but slow to something better, faster, right? Now think back mentally to our pictures from earlier. Logarithmic, log of n, much better in the long run than something like n. So logarithmic better than linear, but we didn't get it for free. What price did we pay to empower Sean to find the number 7 so much more quickly? Yeah. Sure. Question, if you, to summarize for the camera, if you can divide some value by 2 and you get something like 2.5 or 3, you either have to round up or down, but you have to be consistent. And rather than go into the actual code, you have to go one direction or the other. But you have to make sure that you're doing it consistently so that you're not skipping over some element accidentally. So it's a real concern, and it's relatively easily solved by just thinking through the mathematics of what happens, even in special cases like this, and you'll find that it generalizes. Good question. OK, so back to this. We didn't get it for free. What did we pay in order to empower Sean to find 7 more quickly, like fundamentally more quickly? We arranged them, so we sorted them, or I sorted them in advance, but therein lies the potential cost. Right? You can't just assume that the world's going to hand you things that are already sorted if perhaps you need to sort them yourselves. In other words, maybe your approach for finding the number 7 shouldn't just be to take what you're given, but rather pre-process it, so to speak. Massage the data in such a way that it lends itself to a more efficient search process. But that begs the question, how quickly can we sort n elements? How quickly can we sort n elements? I'm going to argue constant time. So I've got n elements arranged in some random order. In fact, let's go ahead and just reveal what these were. So these were some numbers I chose, positive numbers. I pretty much sorted them arbitrarily, just random inputs. Can I sort these in constant time? So it's sort of a trick question. So if there's 8 elements, I, yes, can sort them in constant time, because 8 itself is a constant. But if you sort of generalize, if you've got n elements, can you sort n elements in constant time? Well, no, because if you think about it, well, let's argue I can do it in one step. You can't even look at all n elements in one step. So yes, you might get one element right, but you're going to cross your fingers for the other 7. So just conceptually, you should realize that you've got to at least touch every element once. So what does that suggest the omega notation is, the lower bound is for any sort algorithm here? So probably n, right? Because if minimally you have to at least glance at each of the numbers to make sure it's in the right place, it's going to take you at least n steps. So then that begs the question, the other side, big O. Worst case, what are we talking to sort n elements? Ooh, yeah, so we could go the crazy extreme of n factorial, right? Like, what's one way to sort n elements? Well, let's try all possible permutations, look them over, and pick the right one. Right? And that's n factorial of those, and that's kind of slow. Right? So if you start doing the math, factorial, very bad in the long run. So let's do this. Let's see if we can't figure this out with another demonstration. I, too, have come prepared with 8 pieces of paper. This is a non-talking role, but it is a holding role. I need 8 non-awkward volunteers, please. I see a few. Oh, this guy's being volunteered. You want to come on up? You have to be comfortable on camera. Yep, come on. If you have a hand raised, just come on down until you see too many people coming down, then sit back down. Feels like that's about right. OK. All right. Oh, so you got volunteered, so you are number 1. If you guys want to line up roughly here, you're number 2, number 3, number 4, number 5. Number 6. Oh, wait. Yeah, there we go. Number 7. Oh, next time. All right. So we have 7 volunteers here. Each of them represents a number. So we have an array, or dare say, a byte of volunteers. Your first task is just randomize yourself, if you could. Shuffle. Any old order. And actually, where is our volunteer who walked sadly away? Do you want to come up? I have a Vanna White roll sort of thing for you here. This might be a talking role, though. OK, what is your name? Oscar. OK. All right, welcome. All right, so Oscar's role is to actually sort these n elements, and we, like Sean, are going to critique. So if you can just tell these guys one at a time what you want them to do, let's see if we can't get them in sorted order from 1 to 8. Make them walk every you can tell them to do most anything you want. Very nice. This is an introduction to computer science at Harvard University here. So incidentally, if you ever needed proof of actually going to class, like here, you got videos for your parents here. So could you describe what Oscar did? What was his algorithm? Yeah?
He found the smallest number and put it at the beginning.
Yeah,
And he just kept doing that.
agree? Found the smallest number, put them where they belong, then repeat. Yeah, so it's kind of like he kept walking through the list, selecting, so to speak, the next smallest value. So again, to recap, he sort of, even though he kind of did it by just glancing, we can sort of make it more explicit by claiming that he did this, and he found number 1 somewhere, and he said, go over there, and he put number 1 over here. Then, now that he's got number 1 in place, he kind of looked through the numbers, taking 1 step for every remaining human, finding, oh, the number 2, let's put them into place. ... So now make a statement as to the running time asymptotically, as n grows large, in big O notation. What's the running time of Oscar's algorithm? What's that? About n squared? Why?
He has to take n searches n times. Well, he has to search through n elements n times.
Yeah. That's actually the perfect way of thinking about it. So let's see if we can't make that clear. So worst case, where's the number 1 when they're random? All right, so all the way at the end. So that's like taking 1, 2, 3, ... n steps just to find the right person. It's actually pretty easy now to swap them, because one of the neat features of arrays, as you might have seen or recall from last week, is that you have random access, which means so long as you remember where you want to put something, like I equals 0 or I equals 7, you can swap values, we saw pretty easily, albeit with the use of a temporary variable, or like a temporary placeholder here. But the takeaway is that to find number 1, it took maximally 8 steps. But now he's in place. So now how many steps maximally does it take to find number 2? So n minus 1, so 7 steps, because he can now ignore number 1 and every one to his left and just take maximum of 7 steps. Maybe he gets lucky and, wow, here's number 2. But even there's a catch. Can he stop when he finds number 2 in the general case? Yeah, maybe there's 1.5, right? You kind of, unless you're allowed to make assumptions that these are integers and not, say, real numbers, or that there's only integral gaps between them of size 1, you kind of have to check all the way to the end and say, OK, turns out number 2 that I found way over there was, in fact, the right value. Let me now put number 2 in place. How many steps does it take on the third iteration? n minus 2, then n minus 3, or in other words, 8 plus 7 plus 6 plus 5, or flip it around, 1 plus 2 plus 3 ... plus 8, which actually sums up to, useful trick, right? That thing on the board at top right, behind Oscar's head, m times m plus 1 over 2, which multiply that out. That's m times m. So that's m squared plus m over 2. But per the spirit of those graphs we were showing earlier, when you start to talk really big inputs, who really cares if you're taking a really huge number and leaving it alone, or a really huge number divided by 2, right? The farther and farther you get out on the graph, the more those lines converge anyway. So the rule of thumb we'll generally have when we talk about the running time of algorithms, or these formalities, is that we'll cross out all but the highest ordered term. So in the expression m squared plus m divided by 2, cross off the 2, cross off the plus 1, because it's really just the biggest term that matters in the long run. So can we do better than what Oscar just did? Or can we do differently from what Oscar just did? Would you guys mind shuffling yourselves up once more? Now let's leave Oscar up here, and we can do this sort of by shout-out process. Oh, OK. So we're getting, OK, yes, input from the array. So go ahead, take over here. What do you want us to do? Oscar, do you mind, actually, do you mind, well, we're going to call the swap function. Is that OK? OK. OK, and what's your name?
Chris.
Chris, OK. So, yep, Oscar, swap in there. OK, so Chris is now executing. You should have thought this through, huh? That's OK. You're on the right track, though.
Like the 4 smallest numbers to the left and the 4 biggest numbers to the right.
Oh, interesting. So we could sort of split borrow the same idea from earlier today, split the problem in 2. Now you've got 2 problems half as big. Kind of conceptually suggests, well, maybe we can solve the n equals 4 case a little easier. Although, wait a minute, then we still have the other. So maybe.
Is there a way
Is
what's less than 4 and what's greater than 4?
Good question. Is there a way to find the middle number? Right? Can we pick sort of a pivot value and then just say anyone who's less than 4, go this way. Anyone who's greater than 4, go this way, so that at least we're sort of splitting the problem into size 2, but with smaller numbers on one side, big numbers on the other, because that seems kind of nice. Because then we don't have to worry about merging things together later, right? If you've got some small over here, some small over here, and so forth. Can we find the middle value? Yeah, how long does it take to find the middle value? Right, so n steps. So OK, we got to spend up front n steps. You know, maybe, and we'll get to this later in the course too, that's a lot of people to count. Why don't we just pick a random number? Because odds are, if we know the size of the array, and we know the range of numbers at least, though not necessarily the middle one, statistically, a random number might do a pretty decent job. And if not, if you find that, man, this execution is taking forever, and this quite literally is done in some algorithms, you just quit and then try again with a different random number, because that's the obscure case, right? You try to optimize for the common case. So that's good. And it's actually, I didn't mean to discourage your approach of splitting and merging. You're just kind of stealing my thunder from Wednesday. Because what you were already happening upon is something called merge sort. So in fact, there is an approach along those lines. But just so that we leverage these guys as much as possible, what else could we do?
Instead of just doing one end, when you go through, find the smallest number and find the largest number. Put the largest number on the smallest number.
Oh, interesting optimization. OK, so to recap, when you're going through each of these passes, you know, let's take that approach from day 1 where I was like 2, 4, 6, 8, 10, 12, because that doubled the running time of my counting algorithm. So here on each pass, why not look for the largest and the smallest, because it's very easy to find the extremes, and then just on the next iteration do the same thing with the next smallest, next largest. Is that good, bad, meaningless? Yeah. So good question. Does it actually take any less time? So the swap is probably faster. Moving 2 people around, even with a temporary variable in an array, probably is faster than counting the same people twice as many times. But now let's kind of come back to the formalities. Asymptotically, if you make a claim that this algorithm runs in linear time, and this algorithm runs in n divided by 2 time, should we care when we're talking in the general case? So one takeaway from today is not so much, because you know what? There's a really easy way of making your algorithm run twice as fast, right? Throw 2 CPUs at it, right? No, honestly, like there are certain types of problems, like anything that's constant time, it's so much easier, or it's so easy to just throw hardware at it. And so what we're trying to do, at least when we start to consider these formalities and these algorithmics, is we're trying to stay ahead of that curve. Can we do fundamentally better than just something like a constant time increase? When you divide an algorithm by 2, that's really just a constant factor. And per our sort of request today, we're going to throw away all those factors. So your algorithm too, in the real world, yes, faster. Just like my 2z's counting was twice as fast. But in the real world, and for much larger n's, the students counting themselves logarithmically is going to beat me every day for large enough n. Yeah?
And we sort the way, say you were dealt an end of like 13 cards.
OK.
Random, then you go through, and if you're holding the cards in only one hand, this isn't an alpha.
OK.
If you're holding
Let me stand next to you.
The way you would sort them. So then I think the time of that would be n.
OK. So I missed say it once more.
So you go and look at the first person.
OK.
And put them somewhere. And then go to the second person. And put them in front or behind, depending on.
OK, so rather than go through again and again selecting the person you care about, rather take who you're given at the beginning and, so to speak, insert them where they belong. So that's an interesting approach. So, and I'm using this jargon intentionally. We just described insertion sort, whereas the first version of Oscar's was selection sort. And as promised, Chris's on Wednesday is going to be merge sort. What's the running time going to be of this inserting process, though?
N.
So it's not quite as good. It's not n. Why? What's the catch? Yeah, sure. With the Harvard term. Oh, OK. Hold that thought for just 1 second. Why is it not just n, this insertive process? Yeah. That's the gotcha. Because even as you insert people in the beginning, if you have to insert someone literally into the already sorted list, suppose in the middle of the first 3 people, that's going to incur an additional cost because in an array, you can't just make room. You literally have to pick up the elements and move them over. So with this inserting process, you actually have shifts, like moving someone over, then the next guy over, then over, just to make room that you don't quite see visually with humans because you just kind of make room, right? But if we were really to do it methodically and only let one of you guys move your feet at a time, if we needed to insert Chris, for instance, between Oscar and number 7, we would literally need to move you here, 6 here, 2 here. Henceforth, these are your names for the rest of the semester. 8 over until we finally make room for 5 and 7. So I'll argue, even without justifying it mathematically, it's still actually going to be n squared, roughly. So any other approaches? Yeah?
If we talk to the person next to us, switch with them if they're larger or
Oh, OK. Interesting. And Chris, do you mind if I just move you visually out of the way? So what if we go ahead.
I look at the person next to me. Assuming we want to start from small to large, I look
OK.
at the person next to me. And if she's larger than me, then I switch with her.
Oh, good.
Otherwise, we stay the same.
OK, good. Let me make one modification because we don't have access to 8 CPUs, but just the one. But let's do the same approach. So Chris is.
Comes down the line and looks at 2 people.
Yes.
Switch or not switch.
So I'll steal your algorithm and say, OK, 5 and 7, the first 2 elements, should they be swapped? No. What about 7 and 1? OK, let's swap them. And that can be done in constant time, like 2 steps, maybe 3 if you need a temporary variable. 7 and 3, swap. 7 and 8, 8 and 2, swap. 8 and 6, swap. 8, oh, hey. OK, that's fine. 4 and 8. OK, so now I'm done, yes?
No.
OK, obviously not. But how? OK, so I just walked through the list pointing at maximally n people, or n minus 1 pairs, adjacent pairs. But how many times maximally am I going to have to do that? Roughly another n times, right? Because if in the worst case, number 1 actually started over there, each time we do that swapping, he or she kind of bubbles up 1 position, but only 1 position, because I then move on to the next pair. And so this approach of doing swaps, which there might be n of, but we need to do it n times, still n squared. And so we'll see on Wednesday that we can do fundamentally better. But for now, let's thank these guys for putting themselves through this. We too have some party favors for you, and you all will see on Wednesday. Thank you.